Now let's look at an example. So let's consider a stationary loop that has a changing magnetic field. So let's say that that loop looks like this. So the loop is almost completely closed, but we have one little section on the left where it juts out and we have a little resistor there. So we're going to imagine though that the loop is nearly completely closed, and we're just going to think about how the voltage and current looks in that little part on the left later by comparing the voltage at point 1 and 2. So we have a closed loop. The loop shape is not changing with time, but we are going to have a magnetic field that goes through it. So the magnetic flux density is going to be in the positive z direction. It's going to have some constant value, B naught, multiplied by a sine omega t. So the magnetic field is changing in time on a basis of sine omega t, and it's going to have some be multiplied by some constant B naught. So what we want to do is we want to find the magnetic flux, capital Phi. We want to find the transformer EMF, and we want to determine the polarity of the voltage across points 1 and 2 at time equals 0. So first, let's look at the magnetic flux. So recalling from the previous video, we defined the magnetic flux as phi equals a surface integral of the magnetic flux density dot with some ds. So looking at this, we already know what the magnetic flux density is because that was given to us. And we know that it's some constant multiplied by a time varying magnetic field that's related to sine omega t. So we'll put that part in there. And now we need to figure out what is ds going to be. Well, if we look at our surface, we'll note that the cylindrical coordinates are probably going to be convenient for this problem since it looks like a circle. So now we should figure out what's changing when we move around on the surface. We can see that dr and d phi are going to change as we move around on that surface. So we know that ds is going to contain dr d phi. So if we look at table 3.1, we can see that if we go to the cylindrical coordinates and find the one that has dr d phi, we're going to have ds is equal to z hat r dr d phi. Okay, so we chose ds to be z hat r dr d phi, and so that's pointed up in the positive z direction. So using our right hand, we can put our thumb so that it's pointed along the positive z axis. And we can see that our fingers are going to curl in a direction indicated in red by C. So we have a contour C that our fingers are pointed in. And because our fingers are pointed in that direction, as indicated by contour C, we will always define the VTR as going from positive to negative in the direction that your fingers are pointed. So your fingers will point from positive to negative as defined by your DS chosen by the direction that your thumb is pointed in the Z. So what if you chose a ds that was minus z r dr d phi? Well, in this case, your thumb would be pointed upside down, the contour would be in the opposite direction, and we'll have a slightly different transformer EMF that goes from positive to negative, where the positive is on the bottom, where point 2 was. So this is important because it will be used later in Lenz's law to determine polarity. So what is n? For that surface, right, we have two normals. We have the positive z and the negative z. The positive z is where we point straight up, and the negative z is when it points down, and we have slightly different contours. So as long as you remain self-consistent, you could use either of these, but normally you would probably choose the one in red on the left because that one is the positive z, so the ds is equal to z hat r dr d phi.